Hi, my name is Patrick McDaniel. I'm from the University of Wisconsin. And today I really want to talk about really the last 10 years of AI security research. But I also want to talk more broadly about what the near and possibly long-term effects are and how this will affect our economy and our society. The best way to start is to talk about what everybody's expecting, and that's social disruption at scale. And so what that means is the way we live our lives on this planet is going to change in a very fundamental way over the next 10 years. And I think this was brought most saliently to me some years ago when I was in Germany. I was on a trip with my family, and we were on the Autobahn driving west towards Poland. And we were on the road, and my kids were in the back seat. And next to us, on the far right-hand side was a set of trucks. In the front truck, there was a driver, and all of the trucks behind it had somebody sitting in the driver's seat, but they weren't doing anything. And what I thought was so dangerous is that it was about 2 feet behind them. Sometime later, I realized this was one of the first generations of autonomous driving, and this was called platooning, where you would have a human drive the front car, and all the remaining cars had to do was follow the front truck. And in that moment, I began to understand how this would affect society. And to make it more personal, I'll talk about, I grew up in the 8th poorest county in the United States. It's a little county called Athens, Ohio. That used to be coal country, but the coal in that part of Ohio, it's really on the edge of West Virginia and Kentucky, was so sulfurous, it really wasn't viable. And so in my childhood, and really preceding my childhood, the coal industry collapsed. There was really no reason to be in this rocky terrained county up in the foothills of the Appalachians. But what built up over time was transportation or industry, where it was a great stopover place as goods were moving from the East Coast to places like Chicago in the Midwest, and even as far as Denver and California. And so much of the county was supporting the transport industry. And jobs, there were entire towns that were built up around serving, thousands and thousands and thousands of trucks. And so this became the essence of the county. And so when I saw these trucks in Germany, I began to ask myself a question, well, what will this mean to my county? And so when you think about it, what's going to happen as we move to truly autonomous trucks, because the economics are overwhelming, is that there will be no need to service the actual drivers of these trucks. There will be no need to service the fuel for those trucks, because that'll also be automated in plants along the highway. And then the secondary effects, all the people that serve the diners, and then the people and the doctors that serve the people who work in the diners. And there will be a cascading effect, because the very industry which held this incredibly poor county together will simply vanish in the next 5 to 10 years. And this sounds like a dark story, but it's not really. It's just the evolution of us as a society. And we're going to see this across the board. We're going to see this in paper-heavy industries like healthcare and finance. Most people in the finance industry are moving paper from pile 1 to pile 2. And so that's going to mean massive disruption when the AI world happens. And so what I want to do is start thinking about those people and how this is going to change. But then there's some secondary effects, and I'm going to get to economics a little bit later, about how AI is fundamentally going to reshape us and require us to rethink society and perhaps work itself. But I really want to start by talking about security. I'm a security guy. I've spent the last 30 years thinking about security, and there are always two questions with any technology. The first one is, can the technology be abused by an adversary? And the second one is, can the technology be used against us? And the answer is always yes. So what you have to do is figure out how. And AI is absolutely no different. And so what's important, by the way, at the bottom of these slides, there are papers that are cited, or works of mine and others that sort of talk about these propositions. But before we get to starting to answer the how it can be abused and how it can be used against us, I want to just talk briefly about what is ML. So how this is used in practice as a historical practice is that it's embedded in some kind of system. Autonomous vehicles, since I've already spoken about them, are a good example. The machine learning is embedded in a massively complex control system and network inside of a car. And so that machine learning takes the video images, which are binocular or even more images of the scene around a car, and then identifies objects. For example, the stop sign, as you see here, it uses the input pixels to determine this is a stop sign. Now, machine learning classifies this as a stop sign. Now, this prior to the advancement of machine learning in the last 20 years, this was impossible. It was too complex a phenomenon for us to create a closed form algorithm for. But now it's possible, and we're seeing this in lots and lots of dimensions. But the important point when I want to come back to, it's part of a system, and perhaps that's our savior. Now, the other element of machine learning gets to machine learning to create. That's using things like GANs and advanced versions of this, where we are beginning to create artifacts using AI, which are examples from some phenomenon that we've used to create AI with. And where this becomes really interesting is we're starting to create synthetic reality. If you look at these pictures here, these three pictures look like real human beings. There's a website called thispersondoesnotexist.com. I encourage you to go there. You can set demographics and age, and you will have, this is actually sponsored by NVIDIA, it can create a person that did not exist from literally billions of pictures of other people. Now, we've seen this in lots of contexts. For example, there was a great paper some years ago from the University of Chicago where they were able to create samples of reviews from restaurants using this generative technology. And at the time, we thought, wow, that's kind of a cool trick. Now, flash forward from, I think, 2020 or 2021 when this paper was written to 2026, you go to any website that is doing reviews, it is entirely populated, and I shouldn't say entirely, vastly populated by bots that are using this technology to create fakeness. And perhaps this is going to be an existential problem for us. How do we actually begin to address this? And I want to ask the question a little bit later of how do we move forward when we cannot agree on objective reality, just as a practical matter of society. But also at the same time, just to sort of say, to get to the sort of last major epoch, or the last two, is that as the hardware and software and complexity of these systems has grown, so has its capability. The most prominent version over the last few years has been LLM and originally ChatGPT and now Gemini and Claude and a number of open models, which are not that far behind the commercial models. And those can do incredible things. They're very general purpose systems which you can ask it questions and it can provide some level of at least perceived reasoning about a particular phenomenon, and it'll give you an answer. And that's taken to another level when we move into the new world of agentic systems, where you're now decomposing lots of individual operations or lots of individual tasks or queries into cooperating sets of many versions of these large language models. And every day we see new structures and new architectures which increase the capability of these large language models to do more complex and more utilitarian capabilities. That begs the question. So now we have this amazing technology, but we don't really have a strong sense as a technical community about how vulnerable it is. And so I want to play a game. So you see two pictures here, and those of you who went to kindergarten would be able to identify both of them. You would say, as human beings, because our perception is extremely accurate, the one on the left is a stop sign, but to an advanced image detection system, and I believe this was the Gemini or a predecessor to Gemini, it's actually a yield sign. And the reason for this is the models themselves aren't actually perceiving the way humans are. And in fact, we are being told as a society that we should think about AI as these thinking machines that perceive things in the way we do. And I'll come back to this in a few minutes. And that's not true. And because of that, there is inherent vulnerability. And I'll go back to that in 1 second. But taking this as a matter of computer science, the ability to fool artificial intelligence, to induce it to have some behavior that you want as an adversary, or to get it to say something is something that it's not, is an example of a very known phenomenon called finding the worst case input for your algorithm. This is a very standard computer science problem that's been around since the earliest days of coding systems. And to give you an example, I will go back to this worst case analysis. It actually happened to me a million years ago when I was working for AT&T Research. And so around about 2000, AT&T was the largest ISP in the United States. And oddly enough, one of their largest expenses was actually dealing with email, because disk was really expensive at the time. And so we began to investigate why we were seeing so much spam. And while we had the best-in-class spam detection at the time, we tried to figure out why people were continually able to bypass our systems. And so we began to investigate individual examples of spam. And what we found was there were certain cases where someone's mother in Kansas had their machine hacked, and then the adversary used that machine. And what they did is the following. They would create a spam email, and it's selling Viagra. That was very popular at the time. And what they did is they would send the email, and then what would come back from AT&T was a confidence that that was spam. Now what happened is that they would change something like the word in the subject of the email to v.i.a Viagra and spell it out with dots in the middle. And they would look at, they would then send it, it'd still be rejected, but then there would be another confidence score. And if they determined that the confidence score was decreasing, then they knew each time they were making very small modifications to that spam, it was getting less and less spammy. And all they had to do was change some very very low-level features like changing words or adding spaces and things like that. And what they were able to do through iterations, also known as adaptive attacks, they were able to create a spam that would bypass the spam filter, and then they would send it to all the machines across the country, and then in 1 second we would see thousands and thousands of these. So this is known as an adaptive attack. And so this is basically, they were using this confidence of spam score coming back from AT&T as a gradient. What they were doing is they were learning what makes the algorithm determine whether something is spam or not, and then they would simply exploit that through iterative operations. Now I want to transition to actually moving towards machine learning and show how this example of attacking a spam-based system could be exploited in a similar manner, such as a check caching system. This is coming from something called the MNIST dataset. This is an example of a 1. And what we're going to do is we're going to start with our machine learning algorithm, which has been trained to recognize the digits. This is commonly used in things like banking applications where they're recognizing checks. And so what we're going to do is we're going to do some complex math called a saliency map. And we're going to learn what is most important to the model, which pixel in this diagram of the 4 is most important to 1-ness and 4-ness. So in this case, we're trying to turn our 1 into a 4, and we're going to change that first pixel. And then what we're going to do is we're going to then take the modified image and we're going to give it back to the model, and it's going to give us a confidence score. And that's now our gradient. And so what we're going to do is we're going to do this over and over and over again until the model determines that this is actually a 4. And this is really easy to see in this example because it's black and white digits. But as you saw, it's essentially exactly what we did in our stop sign in our previous example. But what you see here is we only really had to change something like single-digit perception, usually like 2 or 3% of the actual pixels in this case, to change a 1 into a 4. And so what we now know is using a technique like this, if you're an adversary and you are interacting with AI, you can create from a legitimate sample something that humans would determine is indistinguishable from reality, but the model comes up with a different answer. And this is really important because this is what the central security challenge is for us. Machine learning and AI are statistical machines. They will be wrong some of the time. the adversary, if they know where it's wrong some of the time, then they can exploit that. As long as they keep their inputs in the space of things the model's wrong about, then they can be successful. Now, it's always possible. So what's important is that there is no AI that isn't vulnerable to this. If we had a piece of AI or machine learning that wasn't vulnerable to this, then we would have a closed form for the underlying phenomenon. And that's just not realistic, particularly for something like image classification. And so what you'll see here is the two examples where we actually took away pixels on one side and added pixels, and we can get anything to be anything. Now, you'll note that some things kind of get messed up. Like if you look at some of the 8s, turning a 7 to an 8 kind of creates a sample which is pretty obviously sort of damaged. And this is where we need to start thinking about the math. Okay, so what we're doing when we're looking at a problem like this, we have this high dimensional space. High dimensional space is each one of these features in this high dimensional space, and there are decision boundaries on which exist in this space. If certain sets of pixels and certain dimensions are of a certain configuration and they're generally in a region, that's called a decision region. And the things that are most like 1s are in one region, and the things that are most like 2s are in another region. And that's what the optimizer does when it's training the algorithm. It's dividing the decision space in discrete portions of the model. But what's interesting is that if you think about this in like sort of Euclidean distance, these things are some pieces, some 7s and 1s are much closer together than 8s and 7s. And so you really have to do less work to move it from one class to another. And that's true of almost all phenomenon. This has nothing to do with images. This has everything to do with math. So whether you're talking about language, or you're talking about images, or audio signals, or motion in the cosmos, they're all just feature sets within some high dimensional space which you're learning. And so for the same reasons that I described before, they're all vulnerable to these sorts of attacks. And there's different kinds of attacks. Actually, the original attack goes all the way back to about a year before, about 18 months before the JSMA paper, which we wrote, was actually Goodfellow and some other folks, which was the original Panda Gibbon attack, which everyone has seen a million times. And basically, they create an overlay. They create a perturbation vector, matrix, that changes every single pixel within the cover. And what it does is it minimizes the total distance it has to change all of those pixels, so that when you take this cover, this overlay, the actual image itself is very, very difficult to perceive real difference. Okay, so what you're doing is that the adversary in this case controls all of the pixels and will change each one individually. But that's not the end of the story. So it would seem like on the face of it, well, because there's less distortion for perception, actually this is a better attack. But actually that's not true. It's kind of a different attack. And this really gets to threat modeling. So there's two different basically kinds of attacks on AI. There are those which are moving individual features some particular distance, but there's a fewer of them. And things like the JSMA L0 attack is a good example, and there are many others. And then there are the overlay attacks. And the threat difference is that if you're in an overlay attack, you assume the adversary can control every input with extreme precision. Whereas in something like a saliency attack, you assume the adversary can control a small number of features, but do so perhaps moving them a wide distance. And so when we begin to look at models for how we want to defend AI or how vulnerable AI is, we really need to start bifurcating the way we think about threat models from the adversarial standpoint. What can they do? What can they control? What they can't control? And how much? And this led us to some really interesting questions about, is there natural robustness for most phenomenon? And so the first one, I'm in the domain constraint slide, we began to ask the question, this is a PhD dissertation for one of my past students, where we began to ask the question, for a given phenomenon, is there some natural set of constraints that provide robustness of this model? And so let me tell you what a domain constraint is. If you're looking at something like network intrusion or network data, you cannot have a round trip time go negative, because it's not physically possible. So the constraint about network traffic is that all transmission times or round trip times have to be positive, for example. And so we began to ask the question, for any given phenomenon, are the constraints of the domain providing us some natural defenses against some of these attacks, because we're finding these weird regions that the model's wrong. And it not just doesn't apply to something simple like network data, but it also applies to things like images. So when images have to obey, if they're real images and they're not they're not drawn, they have to obey light physics. There is a natural diffusion of light. That's just the nature of light physics. And so if you have a picture where you see massive brightness difference in 2 pixels right next to each other, because of the nature of the physics of diffusion through air, you know manifestly that's a bogus input. And so we began to ask the question, is that actually a defense? And it turns out it sort of is. But unfortunately, as soon as the adversary knows the constraints, what they can do is that they can pull the adversarial sample back into compliance with the constraints. So it turns out that there is no natural robustness for a phenomenon. And this led us some work I did with some folks at Stanford, where we began to ask the question, so, okay, let's take a step back, and in the threat model, if I'm an adversary and I've got a sample, can I attack the system if I can only control a number of features? And so we began to do an evaluation that asked, how many different directions do adversarial samples lie in a given phenomenon? And so we found for this color data set, I'm blanking on the name of the data set, but we found that for most input samples, we could find adversarial samples in something like 20 dimensions of something. I believe this is a 128 dimension system. Or no, I think it's 256. So really, there's a huge number of features you can change to get adversarial samples. There's no natural robustness. But it somehow gets worse because models are incredibly biased. So this is the texture work that another PhD, Blaine Hoke, who's moving to the University of Texas at Dallas here, began to explore. She began to say, well, is vulnerability driven by natural occurrence of underlying feature patterns? And in the vision domain, this is textures, right? And so what this work did is it began to explore, are models biased by some underlying phenomenon which isn't the thing we're actually trying to classify? And so we began looking at textures because there was some good literature on how our human perception differs from perception of AI, largely because the AI systems are designed for the lower levels of our comprehension. And she's actually a biomedical engineer by training and had some really interesting results here. But the bottom line here, if you look, we call this the alligator graph. If you look at this graph, what you see on the top edge, and it basically says that if a particular image that we're presenting to an image classification system has the dominant texture for that texture class, that is, that the highest frequency texture you will see in that texture class, then the model was extremely accurate. But if not, it was not accurate. And so what that tells us is the models themselves aren't actually perceiving the objects, but they're perceiving lower level features like the presence of textures. And while I don't have a slide on this, we have a follow-on work that we're submitting on Monday that shows that we can actually exploit this. I don't even have to know anything. I can just layer over certain kinds of textures and get models to just completely misclassify things, even with very, very low frequency. We have a problem in the security community is no one actually has a good definition of what it means to be secure. that we've been talking, there's been a lot of work, and Ian Goodfellow, I believe, said to me that it was never intended for norms to be a security measure. It just sort of happened. There's really the 4 norms that everybody uses, and we all try to do things like define security as the existence of an adversarial sample within a norm ball of our original sample. And that basically means, is there anything close to this? And of course, that's not a really useful, just as a practical security exogen, why is one feature dimension have anything to do with is one feature dimension exactly equivalent in terms of security controllability or a security risk the same as any other? Well, of course not. And so these notion that norms are actually the right way to even think about security is inherently flawed. And so there's sort of this religious war about what are the metrics for security in AI. So I want to go back to Claude Shannon and information theory and say anytime an algorithm tells you anything, it tells you that's based on the data, then it tells you something about the data itself. And so this is, there's a black box attack paper that I wrote, I believe, in 2019 with some other folks, which basically exploited the notion of transferability. And without getting into too much detail, if I can talk to the model, I can extract the decision boundaries. And I think it's sort of obvious how you do that. You basically just use a standard search technique. And it turns out these models are pretty easily extracted. And all you have to do is if you understand the decision boundaries and you have samples that are on either side of the decision boundaries, you can recreate a proxy of that model, of what's called a surrogate model, of the model. And then if you launch one of these white box attacks against the surrogate model, it automatically works on the other model. And so that's actually a black box attack. You don't even have to know anything about the architecture or even the kind of machine learning you're actually using to actually attack it. As a model exposes, as it responds to you, it's telling you something more and more and more about the underlying data. And we don't know how much information it's actually exposing. And so this leads to all sorts of interesting problems. That is, if you have an adversary-facing system, they have a ready ability to perform reconnaissance. If I can talk to a machine learning algorithm that's doing, say, intrusion detection, I can use that model to simply infer what it's actually doing, and then I know exactly what it's doing, and I can construct an attack that bypasses all of those protections. There are other problems. There's a lot of companies that are building AI with billions of dollars of data, but as soon as I can interact with that model, I can extract some part of that $1 billion. And there's a whole body of research on things like a membership attacks, and there's a whole bunch of theory around things like differential privacy, which begin to reason about what the information flow is from these systems. But what we do know is that anytime you are given input-output pairs for any model, you know something about that model. And we don't know how that can be exploited. So if you're building a business on being safe, or you're building a business financially that requires the adversary never learn what your data was or what your model is, as a matter of practicality, you're going to lose that war eventually. And then finally, privacy. We are all having our data sucked up and pulled into these models. I think we could have a long conversation about to what degree we have any agency in stopping it. But as the data goes into these models, there are real deep privacy concerns. We need to ask ourselves how much of our personal data is actually being exposed through the use of this model in ways that could be actionable by others to affect me. And there's some common examples of things like insurance, things like if medical models are built on your data, insurance company can extract potentially what your medical history is and then use that to make pricing or coverage decisions. But there's even some more basic problems that we have today. We spend a lot of time in the academic security community, and certainly largely in the AI and machine learning community, coming with different architectures and algorithms. But the reality is perhaps the best path to having better models and more accurate and safer models is to have better data. We need better science of the curation of data. We need to know how to look at the distribution of training data, certainly the distribution of fine-tuning data, and know what the influence is on that model, and to know where gaps in that data are making that model actually vulnerable. But there's also, lots of other questions about just how we use AI. So we've spent collectively probably trillions of dollars training all of our language models, and yet they are a testament to time, what parts of that data are actually still relevant? What are the facts that are being ingested into these large language models that are still true? So most interesting phenomenon are actually non-stationary. So we don't actually figure out when we want to retrain model, when we pull data out. And unless we do that, what we're going to see is the quality is going to age over time. And so there's a secondary consequence of this that I think that the people that are investing massive amounts of money in these large companies is that we are not paying one time to train one of these LLMs. This has to be an ongoing and forever problem. And we're really good at putting things in these models, but we never pull anything out, and we don't know what to retire when we need to. There's other societal questions, and I'm going to get to those in a moment. But models are making consequential decisions. I was in a room with no windows in a three-letter agency discussion that was between the DoD and some intelligence community, and we were talking about autonomous weapons. And I'm not disclosing anything particularly interesting, but there was a discussion on whether they wanted to have AI do targeting. So you think something like a Black Hawk helicopter's got a Vulcan on the front. This is a gun that unloads, 2,000 rounds per minute, can liquefy a human in milliseconds. It's one of the most dangerous weapons in existence. And so there's a pilot and there's a gunner. And the gunner has the most consequential job in the cavalry, the air cav, because they make what are called friend or foe decisions. So think about it this way. There's three guys standing on a corner. One has a surface-to-air missile. Black Hawk comes around the corner and has to make a decision. And he has something like 500 milliseconds to decide whether to pull the trigger. All three of those guys are dead, or not pull the trigger, and that guy gets that thing on his shoulder and launches, and Black Hawk's dead. So that is the classical military friend or foe decision that they've been fighting since people, threw the first rock. But where this hits with AI is there was a discussion, what if our targeting system can target them and have a better friend or foe decision, and it can do so in, half of the time with 95% more accuracy. And everybody's like, oh, that's kind of a good idea. And I was like, sort of wrapping my head around it. And there was a colonel who stood up and he said the following. He said, listen, every time someone dies in my company, I have to write their parents about how that soldier died. And I have to explain to them what happened. If there's an operational problem or if it was just normal combat or whatever. And he says, I cannot send somebody's mom a letter saying the AI messed up. So, in that moment, I began to understand that there are some human-scale decisions we just have to accept as human beings, as an ethical exogen. We cannot avoid the messy stuff of life by replacing it with AI. Because at that point, we're subjugating ourselves to that AI, and we're basically being unethical, even if it's more accurate. And so this is going to be a real open question. I've spent a lot of time in hospitals and things like that, and there are some really very gray areas. But things like whether a soldier lives or dies, at least in my mind, doesn't seem like a gray area. That's a question where the gunner's job is one of the hardest in the military, and that's just a fact of life. And there are many things like that. Who gets a home loan? Who gets into a school? And I'll talk about that in a moment. And so these models, when they're used for surrogate of important societal decision-making, we cannot accept that. But even when they're used in things that are maybe not so weighty, we need to think about all of the other problems about bias and unfairness and all of those other things, which really have been focused on in the academic space, but we have not seen it really taking up in more than frankly, in my mind, I could be wrong, than a superficial way in industry. And it gets even more complicated when we move to large language models. Large language models often have 1 trillion or more inputs. We do not possess the mathematical framework as a species to reason about anything with 1 trillion inputs. And so it is going to be a magic box for some time. And this has lots of well-documented consequences, things like hallucinations. And the use of these LMs is so tantalizing, it's now creating other societal problems. I see this more prevalent in things like in education, where we see an entire generation of people, of younger kids, which can do their homework no one ever wanted to do, or they can use AI for 5 minutes and they don't do it. And I have had long conversations with educators about that. And we're going to see that replicate over and over again, that there are certain things that we need to be doing as humans for good health and good minds and good society that we won't be doing because we can just simply avoid the hard work of being a human by using one of these LLMs. So lastly, I want to talk a little bit about society. In order to do that, I have to start with Charles Goodhart. So he's one of the most famous economists that ever lived, but he has the famous Goodhart's law, and it says when a measure becomes a target, it ceases to be a good measure. And so this basically, to think about this, think about miles per gallon, right? So in the 1960s and 1970s, there was a movement here in the United States, and then it sort of spread to other parts of the world to create greener cars. And so in that time, there was the miles per gallon was accepted as a measure of how much environmental impact a particular car would have. And what Charles Goodhart was saying with this quote is that something like miles per gallon fails because it becomes the target. And I'll tell you what I mean there is that everybody builds cars to bit greater miles per gallon, but they ignore all of the other costs associated with cars. Tires are awful for the environment. They're giant crayons creating, basically rubber dust everywhere, which can be toxic for lots of things. It's just awful. The paint is fantastic for keeping away rust, but it is really nasty. The heavy metals, these are all basically rolling computers today. All of these other environmental effects are completely ignored because we told the auto industry, look at miles per gallon, maximize that, and then you'll have a good environmentally a sound car. And I think the same thing is going to happen with AI. And I would say there's a corollary. When model becomes a target, the target becomes vulnerable. So let me ask a question. What does it take to be a good applicant to the University of Wisconsin? Right? Now let's do something more interesting. Let's make fun of Harvard. To get into Harvard. And so the obvious question, if I asked an average collection of people, they said, oh, well, this is, your GPA or your personal statement or your activities. But what we learned from the earlier part of this talk is that's not actually. If AI is used to do admissions for Harvard, and they'd love to use it because it would get them out of a lot of legal challenges that they're facing right now, what would be the thing that would get you into Harvard? Probably be something like varsity tennis. White, rich, Northeastern, right? And where I'm going with this is that every time we create AI and we put it in place of a human scale decision making, people will find out what makes the model happy. People will not be good applicants to Harvard anymore. They will figure out, I need to do this, and I need to go to a Protestant church, and I need to do this and this and this, which have nothing to do, well, I wouldn't say nothing to do, but they're not indicative as the most important features. And we can try to fine tune, but it turns out fine tuning only gets you so far. And so as a society, when we begin to deploy AI, we really got to start having some hard conversations about where can we use this. And this actually leads to the death of incentives. The death of incentives. When you use AI, the underlying incentives you're trying to promote go away because there's an easier way to get there. And we're going to see this over. We see this, people were using it for things like sentencing in Pennsylvania, which was like insane in my mind. So we're going to see this over and over. And the problem is these are tantalizingly hard problems we're trying to solve with AI. And it would be just so much less icky if we didn't have to deal with it. But that's just not the hard stuff of life, and we're just going to have to accept that. So I want to move back to our synthetic universe, because this is sort of existential for us. What if we can't agree on reality? Right? I've seen this most recently. There was some elections in Wisconsin, and for the lowest level elections, we were seeing deep fakes that were pretty good. And so the objective things that the candidates were saying was very much up in the air. And so we have to actually really begin to ask ourselves some hard questions about how do we adjudicate anything in that space. There is no real policy here, and I'll come back to that a little bit later. But I actually want to take it one step further. I'll tell you my nightmare scenario. My kids are, thank God, out of high school recently. And it's a shark tank. It's an awful place. And it's not because kids are bad, it's they're in a developmental phase called pre-consequence. And so they don't actually understand what the consequences of their actions are. But where this is going with AI, so let's take a girl from my county. It's a, terrible home situation. She's unpopular, she's alone. And then she gets in a fight with some mean girl in her school. And that girl then downloads a bot off of the dark web. And this bot creates an identity that gets into social media, contacts all of her friends, makes across digital media, and then targets her and creates things she says and artifacts that claims, and now she kills herself. Within the next couple years, somebody's going to be able to download that bot and create 1 billion of them in 10 seconds. What are we going to do when we have the capability to weaponize fake human beings against each other in the next few years? There are no laws and there's no policy because forces that be are not looking down the road at the societal problems that are going to happen when this day comes. I want to go through a couple basic misconceptions I believe are really prevalent right now around AI. First one is the AI rejection fallacy, which I just sort of named. And that is, when I talk to people in the AI space and spend time in Silicon Valley and the cognoscenti, there's this constant drumbeat of, the public is rejecting AI because they're afraid for their jobs. And I would say, no, that's not actually why they're rejecting it. They're rejecting it because they don't trust it. Big tech has delivered one generation of technology after the other, and people's lives have not gotten better. They've been scammed, and you can see the effects of social media on kids. We've lost our attention. We've had our democracy hacked. There have been over and over, we've seen example after example after example where technology is not making our life better. And now here's this thing, it's going to take your jobs and all of this, and by the way, it's good for you. No one believes that. Sure, some people believe that, but that's not actually why it's being rejected. People don't want it. They don't trust it, and they shouldn't. There's no reason to trust it. And that gets to the second point, which is AI isn't built for you. When you use AI, that thing wasn't built for you. It's built for the company that sells you the tokens. Do you believe that there is no one of the major providers that if I went to them and said, listen, if you promote my product over everything else when you're responding to this AI query, you won't do it? And if you say, no, they won't do that, let me remind you of search. Search has become arbitrage. You're not actually searching anymore. You're throwing it up and saying, who will make money off my asking? And I will just take whatever you give me because I don't have a choice. This is going to happen again. And the worst, it actually devolves when you start talking about agents. In the agent space, the vision is, and I go to these meetings and they're like, there'll be 30 companies, each with their own agents, and they'll be interacting to facilitate your travel plans. There's no traceability. There's no accountability. They're at odds with each other, and none of them is actually looking out for you, right? Their job is to extract the maximum amount of money out of you, not to actually give you good travel plans. And so as you metastasize across lots of unknown, mysterious companies, it's only going to get worse. And so we're not going to have good outcomes unless we just sort of accept our fate, which I think is a mistake as a society. And we've, by and large, sort of accepted our fate around social media and search, but this might have much more consequential impacts. So, what's next? Generalized artificial intelligence. It's basically just take what you have now, and it continues to evolve, and it can do basically anything a human can. There's been a lot of heat and light around this. I think it's very much a controversial topic about exactly how that's going to play out in practice and what the actual utility is going to be. But I actually would like to talk a little bit about this GAI extinction event. A bunch of people got together, some CEOs and some technical people, and they said, this is a real threat to humanity. And I go, no, it's not. right? I mean, only if we are the most irresponsible stewards of AI would this actually be true. And I feel like this discussion about the human extinction event is really preventing us from talking about the kitchen table problems this is creating. And it's a great way to virtue signal to the world that you care about the consequences of AI without actually doing anything. Where it's going to affect people is in their social interactions, in the consequences of the quality of service that they're going to see in their lives. Don't waste my time with this nonsense. Please have the discussion about the kitchen table issues that are going to matter within AI. So, it's pretty dark. Paint. But this is just evolution. We've been through this, right? We got farming, and we got the printing press. Industrial Revolution were major shifts in life on this planet. This is just the next one. The people that adapt will succeed and flourish, and people that don't won't, and it's happened every single time there's been one of these major shifts. But at every point, there's been winners and losers. And right now, from where I'm sitting, and for what it's worth, and I'll editorialize because I can, is if I look at the sum winners in the way we've set up the game today, is so small compared to the losers that this potentially has the ability not to be good for society at large, because we are, again, not really being honest with ourselves about the challenges. But all of this is going to require us to do what we're really good at. We evolved as a species to be the most dominant creature on this planet because of our constant ability to innovate. And so we have to innovate ourselves out of these problems, and we will. It's going to happen. And we just have to be honest with ourselves and approach it as such. Now, the good news is machine learning and AI is just a component. I'll go back to my second slide or so. When I was talking about AI as a component in a system in this car, it's just a component. We have been building secure, trustworthy systems out of insecure components for 800 years. It's called engineering. So what we have to do is we have to go back to the drawing board and say, how do we engineer systems that will prevent these ills? And then finally, as a final note, we should really start talking about policy. We are letting companies, because so many zeros are involved, essentially proceed without any governance, without any consequences. And so we as a society have to get together and decide what the rules are. Because if we don't, and we just leave it to people whose sole motivation is money, we are not going to have a very gentle landing for AI. So with that, I'll say thank you, and just some reading. There's a couple documents. There's a national strategy document that I think we'll put on the website that we created in 2019 about the security of AI and how AI can improve security. And there's another document about how security and AI go together. It's called the SATC 2.0 document that really provides a roadmap for security for the next 10 years. So with that, I'll say thank you and take some questions.
Thanks, Patrick. That was a great talk. I think you surprised us all in many ways, and a lot of your thinking resonates with us a little too deeply. At BIML, we've been concerned about what happens to models that are constructed from public data out there in the huge ocean of data on the internet that then loop their output back into the data ocean and get sucked back into a training set in a feedback loop when the original data was wrong or bad or biased or poisonous or whatever kind of term you want to use there. We call that recursive pollution. And as you know, in academia, that's been talked about as model collapse because that's the ultimate end state. But what do you think really about this recursive pollution thing? Are we just kind of nuts at BIML? Because we're
no, I think that's absolutely true. I mean, there's, you add dead internet theory to AI is being used to train AI. I think the problem is that people are lazy. So we found all of the data, and rather than figure out how to take what we have and use that as a refinement process. They just go and find things that look new, right? And so that model collapse, you know, is an amplification attack, right? That's basically, you know, it's just the two microphones, you know, in the same room. It just bounces back and forth. And so we're actually seeing that now. And there's some interesting work that's been done about like identifying some of that amplification. But I think the reality is that we have to not get more data, we got to get better at using the data we got. And that requires, you know, I talked about data curation as being kind of like the missing science to all of this. Like I am blown away, and frankly I have a hard time keeping up with all of the amazing architectures and techniques and structures and RAGs and all that other stuff, which is all great, but we're still starting from a very vanilla version of the data. And we do some curation, but there isn't a real solid science about it. And again, I would call all of the problems with bad curation creates amplification. For anything that's non-stationary, things get old, and then your model then can get conflicting information, and then it's flip a coin. So there's so many effects when we don't get more and more and more data. We already have it all, essentially. Right? We need to use the data we've got better, and we need to get really rigorous about that.
Yeah, I think to dovetail on that, our thought around what we term Beigification, what that ultimately will result in on a societal level, right? When you mentioned young people coming through the academic rigor, speak a little bit about that, maybe.
Sure. So what you're talking about is a race to the middle. It's basically what you're doing is, as the only sources of data for people to consume are the things that are most appreciated by the model, you then have the model reinforce itself, and then there isn't anybody saying anything about anything outside of that, and so the distribution gets thinner and thinner and thinner. And if we're not actually learning things outside the model, it gets thinner and thinner and thinner, and then we're just regurgitating what's in the model, whether it's right or not. And so that's a real problem that really results from over-reliance on AI, right? And that's sort of sacrilege in places right now. It's like, well, do we really need to be doing AI for everything, right? I mean, sure, you want to organize my files, fine, but do we need it for everything? And the answer is no, because where are we going to get the next great musician if all they hear is fewer and fewer and fewer bits of music?
Well, and that's where the Beigification term comes from. You remember when the astrophysicist calculated that the color of the universe was
beige? Yeah. I do remember that. Yeah.
Well, it turns out that that's what you're going to get if you average it all together.
Yeah, well, and they're big averaging machines. Essentially, I mean, that's the reality. Yeah. And if we just become parrots to the, you know, so the reliance, you know, the assumed reliance is we feed it data and it learns, but now we feed it data and now it feeds us, and so that's probably not so good. You're not going to get a lot of original thought there.
Yeah, well, a couple comments. One is I think that Patrick's take on the concept of recursive pollution by introducing the concept of amplification is really quite interesting. It's a great addition to the way that we've been thinking about this, because our concept suggests that it's kind of a slow accreting process, whereas amplification and feedback really suggest that it might be a lot faster than we expect. The other thing that continues to resonate in my head is that at some point in your talk you were saying one of the things that has ensured and promoted our success and our survival is innovation. And I think that innovation often happens in the context of cooperation. In fact, some people also talk about the superpower of humans as being extremely cooperative. Mm-hmm. So if we need to cooperate in order to innovate, where are we? What is AI doing to this aspect of the environment, and how can we avoid the worst case scenario of everybody just talking to a bot and getting to this and having no new ideas?
You're actually really put your finger on a really important problem. And that is the value system we had prior to AI doesn't work anymore. How we value artifacts created by humans. So right now, this is a problem in academia. Somebody that sits in a lab and uses Claude or ChatGPT or Gemini to create a paper that writes as well as I can, I'd like to believe I'm an okay writer, can write something as good as I, and take bad ideas and bad science and make it look amazing, and then it gets submitted, and it's up against my paper, which I hand wrote. Mine takes 6 months. That took an afternoon. That person is going to have vastly more productivity than me. Well, they're not really innovating, but they're actually creating the artifacts that look like innovation. And so we have a problem, and I'm using academia, but it's going to happen everywhere, right? We see this in the publication industry. There's so many books being submitted to the publishers, they can't even figure out how to sort through them. And so we as a society, we as a species, have to figure out how to rethink how we evaluate people's productivity. Because if it can just be done by AI and look indistinguishable from someone else, at least to somebody who's not really paying attention, then all of our merit systems kind of break down, right? And what are we going to do, right? And we're going to see it over and over again. I mean, we see it now,
yeah,
right?
So on these bright notes, well, thank you again for coming. This has been extremely interesting, and we're very proud to have sponsored your first talk in the barn.
A first talk in a barn. And let me say thank you for inviting me. It's been a real joy.
Treated me like something that you left behind to stay. Now I'm not sure that I can give a damn.